Hey guys, I'm going to cover the Unit 1 Progress Check D. Um, I know my audio probably doesn't sound too great. I'm not on my usual setup, and so I apologize for that. Um, okay, but starting off here, we have a calculator question. We're given a function, and we're told to use the intermediate value theorem on the interval from 10 to 15. And the intermediate value theorem says that if we are continuous on an interval, so meaning x interval, so from x equals 10 to x equals 15, then we're guaranteed every output, every y value between f of 10 and f of 15. And so what we want to do here is basically we're just trying to see which of these four values, so negative 15, 0, 5, 15, are going to be in between the y values at x equals 10 and x equals 15. That's what we're trying to guarantee. So there are two ways you can go about this. So what you could do is just evaluate the function at x equals 10, and you can do something like that. So if you do 10 store as x right here in your calculator, so I'm using the bottom left corner button right above the on button. It should be for you guys. It looks like an arrow, I think. But if I do 10 store as my variable, what happens now, so like the first part of the question was 2x, right? So it was 2x. Well, 2 times x, in this case, x is representing 10, so that's going to be 20. But if you do 2x plus, tangent, I think it was, tangent of x divided by 5, and then minus 15, you're going to get 2.815. So that is the y value at x equals 10. You can do the same thing at the y value at x equals 15, and then you can check and verify which of these values is going to be in between those values right there. And so that's one way you can do it. Another way you could do it is by graphing the function and then using your table to see the x and the y values of at x equals 10 and x equals 15. So that's another way you can do it, but you're just trying to verify which of these values will be in between the y values of x equals 10 and x equals 15. So the function h is defined by, given there, which of the following statements must be true? So what would I do here? It looks like it's trying to use definitions of asymptotes and vertical asymptotes at that. Because I can look at like all of these options, you're evaluating the limit as x approaches 4 from the left and from the right, and the output of the limit is infinity. So that's a vertical asymptote. Now you just have to know which one of these is correct. So you can see from the expression that there's not going to be a factor of x minus 4 in the numerator. And so that means x minus 4 is not a removable factor, which means it is a vertical asymptote. So with that being said, you just need to check both sides of x equals 4. I'll give you an example of how you can do that. Let me pull open Notability here. So the expression was x squared minus 9 over x minus 4. So we're going to pick a number very, very close to 4 to the left and to the right. So if I'm evaluating the limit as x approaches 4 from the left of this expression right here, we'll call it f of x, or I think in the question it was h of x, right? We'll call it h of x, right? That's going to be equal to, so let's pick a number very, very close to the left of 4. So that would be like 3.99999, something like that. Now, if I plug 3.9999 into this expression, that's going to give me something close to 16, right? Because it's pretty much like we're plugging in 4. And so whatever it is, that's going to remain positive. So that's going to be a positive value over. Now, if I plug in something Very, very close to 4 from the left here, though. From the left side, that's going to make it negative, because anything less than 4 here would mean that we're subtracting something greater than that value, so that would be negative, meaning that we get a negative value. So that's got to be negative infinity that we're approaching. And so you can do the same thing with the limit as x approaches 4 from the right of h of x. Okay. One thing I want to note here, I think we'll talk about in class. I can't really say for sure because we haven't really had this discussion yet. But if I were to try to plug in just regular 4 here, I would get some number over 0, right? I would get 16 minus 9 over 0. This is usually an indicator. If you have the denominator here as 0, but a number on top, that's an indicator that you are approaching an infinite value. Okay, so keep that in mind. Anytime you have a value divided by 0 by substitution, whenever trying to evaluate a limit, that's an indicator that it's approaching infinity of some sort, positive or negative, but you are the one that has to check if it's positive or negative. Okay. All right, so that should do that there. Okay. Let f be the function such that the limit as x approaches 3 from the left of f of x is equal to infinity. So I know I have, well, I can't, yep. What do we have at x equals 3 then, if that's the case? There's a definition of vertical asymptote, right? So that one should be pretty easy. Let f be a function of x if the limit as x approaches 2 from the left is equal to positive infinity, and the limit as x approaches 2 from the right is positive infinity, which of the following could be the graph. Yeah, I think this one should be pretty straightforward for you guys. Just trying to see from the left and from the right of 2, they're approaching infinity. Question 11, let f be the function defined here. Which of the following statements are true? As the graph has a horizontal asymptote at y equals 3. So how do you check for horizontal asymptotes? Well, these are two rational expressions. So we have a linear over a linear. Now, they do have the same degree. It's 3x as the leading term on the numerator and x as the leading term on the denominator. So you just need the coefficients of those, the ratio of the coefficients, and that will tell you horizontal asymptotes there. Okay, and that would be honestly for positive and negative infinity as x approaches either direction. Okay, and then let's see what else we've got. That should take care of 1 and 2, by the way, if you're reading those. And then the graph of f has a vertical asymptote at x equals -2. Okay, so the vertical asymptotes in this case will just depend on non-removable factors from the denominator. And I don't think we can remove any factors in the denominator here, so we do have a vertical asymptote, okay? All right, the population on an island is modeled by P of t equal to 5,000 over 20 plus 30 e, okay, for t is greater than or equal to 0, where P of t is the number of people on the island after t years. What is the limit as t approaches infinity of P of t? Okay, so we're pretty much just trying to find what the horizontal asymptote is on the as t approaches infinity. And so the only thing you're really just trying to evaluate what the function is doing at infinity, right? So if you go to this expression right here, and there's only one spot for t, and that's going to be in the denominator in the exponent of that right there. So I'm going to come into Notability. I'm going to write down this expression. So P of t is equal to 5,000 over 20 plus 30 e to the negative 0.03t. And if I plug in infinity, what I'm trying to do is analyze what's going to do, what kind of effect will that have on this expression? Well, the numerator is constant. It's never going to change. So what's going to happen to the denominator? Is it always going to get larger or is it going to get smaller? Um, and how by how much? So that's what we're looking. So this is constant. Now 20 is also constant. So this term is going to make all the difference, okay? Um, Also notice here that if I plug in an infinitely large number here, let's put it in like negative 100,000 or something like that. Um, Sorry, plug in 100,000. We want infinitely large. So if I plug in 100,000 right here, note that that's going to make this expression negative. And if I have e to the negative value, something like that right there, so this would be 30 times e to that negative value, which would make that the same thing as 30 over e to that positive value. So essentially thinking about it, if I'm plugging in an infinitely large number here, like 100, we can do, 1 million. If I plug in something like that here, well, what's that going to do is it's actually going to be the same thing as if I'm plugging in 1 million here. Now, if I have an infinitely large number on my denominator and a constant in my numerator, this thing is just going to go to 0. So this will just be equal to 0 if this gets larger and larger and larger. So that means that this expression right here is going to become 0, right? And these are constant. These are always going to stay the same. So that should be what we get. So if we let t go to infinity, essentially what we're saying is that this term doesn't matter. It's going to be gone. And these are going to stay as t gets infinitely large. So that should give you an idea of what the expression should be. Okay? So let f be the function defined by f of x equals, all right there, for x greater than 0, which of the following is a horizontal asymptote of the graph of f? All right, so similarly, we're just evaluating as t approaches infinity, right? So we have f of x is equal to 5x to the 20th power over 8ex plus 9x to the 20th. Now, these polynomials right here, polynomial expressions, are growing at the same rate. They really don't. They're gonna grow at the same rate. They have the same power, and it doesn't really matter the coefficients that are being multiplied by them. That won't have too much of an effect. The fact that they're to the same power, though, means that they're going to grow at the same rate. So the only difference between the numerator and the denominator then is this expression. So what is this expression going to do? Is it going to make the denominator grow faster than the numerator? Well, if these are growing the same, now e to the x grows much faster. Exponentials grow much faster than polynomials do. And so, yeah, the denominator here is going to grow much faster considering that these will grow at a very similar rate. And so, but adding this to this would make it so that the denominator here is going to grow much faster. And if the denominator grows faster than the numerator, then the expression as x approaches infinity will approach 0. Anytime a denominator gets larger than the numerator, the expression is going to approach 0. So that should answer your question there. Let f be a function such that f of 3 is less than 4 is less than f of 5. Let me try and give you a visual on what that means right there. So we're on the interval from 3 to 5 on the x-axis, right? We're saying that we have f of 3, so there's going to be a value of 4 here. So let's say f of 3, and let's say f of 5. So, like the expression said, f of 3 was less than 4 was less than f of 5. What did it say? Which of the following statements provides sufficient additional information to conclude that there is a value x equals c in the interval from 3 to 5 such that f of c is 4? So, is there a value somewhere in here called c that will give me the y value of 4? Now, that's only possible. Remember, the intermediate value theorem basically just has one condition: needs to be continuous. Function needs to be continuous on the interval. And so, if it is, then yes, there will be a value c in between here that will have the y value of 4. So, only condition that you need. So check the statements here for that condition. And last question, let f be a function of x. Which of the following statements, if true, would guarantee that there is a number c in the interval from -5 to 4 such that f of c is 12? All right, we just said that, right? We need to be continuous, so that's going to be option C or option D. Now you just need to make sure that 12 is in between the y values, okay? And that should be it for this progress check. Hope it helps.